Application of Maclaurin and the Radian measure. In your companion, you will see that there in chapter 1, section 1, are two examples of the application or where we will be using Maclaurin and the Radian measure. In the first one, we are going to determine the area trapped or the area of air trapped inside of the cylindrical shaped fish tank. Now, the information provided is the following. They say the circumference is 1 meter. They say that the depth of this fish tank is 90 centimeters and that the height of the water is 30 centimeters. Now, if I look at the face area of this cylindrical container, I see that this face area over here specifically is an area of a sector, right? So that's going to be important now. Now, let's see why. If you are calculating a volume and the volume is shaped by taking a two-dimensional area and lifting it out from the surface, thereby creating a three-dimensional volume. As you can see, it is uniform. It remains the same for the entire stretch as I lift it out of the surface. That is referred to as a uniform body. If you're calculating the volume of a uniform body, it is determined by this volume or by this formula. Volume is that face area that you see, the turquoise area, times the depth or the amount by which you are raising this face area out from the surface. And this is exactly what we have here. We have a face area. Let me maybe just enlarge it over here. We've got a face area and we are lifting it 90 centimeters from the surface. So that's how we will be calculating the volume, the face area times the depth, and in this case the face area looks to be a segment. So that's what we are going for. Now, how are we going to calculate that face area that is required in my volume calculation? What I've done is I've taken the front part or the circular part, there it is, and I'm going to work with this. Right, so I know that the circumference is 1 meter, which is 100 centimeters. I also know that the formula for circumference is 2 pi r. So that gives me a way to calculate the radius of this circular face as being 15.92 centimeters. The next thing I'm going to require, because if you know that, or if you have read the note, you will know that if you're calculating the area of a segment, you will need to know what the angle theta here is, right? What's that angle there? And the only way that we're going to get that right is if we know what this value of h is that I show here in my diagram. Now that's actually a very easy calculation because they told us that the depth of the water is 30 centimeters. And I know that my radius is 15.92 centimeters. So if I subtract those two from each other, that h value is 14. Now I can use my trig relationships to calculate that angle. I'm going to say that the entire angle is theta, therefore the angle on the left is theta over 2 and the angle on the right is theta over 2 as I indicate over here on this diagram. Now let's see. Cos of theta over 2 is adjacent, which is my h, over my r, or my hypotenuse, which is r, and I can calculate that as 0.88. Now there's a booby trap here. They say that the calculator I have does not have the trigonometric functions on it. And then it advises us to use the Maclaurin expansion until the second term. Now, cos of theta, if you look in your notes, you will see that the Maclaurin expansion is 1 minus theta squared over 2. But that's cos of theta. I require cos of theta over 2. So I'm going to substitute all the thetas in this expression with theta over 2. And when I do that and simplify, I find it as 1 minus theta squared over 8. So if I now go back to my equation where I had that cos of theta over 2 was 0.88, I'm instead going to replace my cos of theta over 2 in terms of its Maclaurin approximation. Solving theta from this equation, 0.98 radians. Right, so now I can continue with my area calculation of this segment, half r squared theta minus sine theta. And I substitute my 0.98 in and I see that I've got a second problem here. I don't have a sine function on my calculator. So now it also says use Maclaurin. Now sine of theta, if you look in your notes, is theta minus theta cubed over 3 factorial. If I do that, I calculate it to be 0.82. So I now know everything I need to do this area of the segment calculation. I find it to be 20.48 square centimeters. Volume calculation, since this is a uniform body, here's my air trap, right? So that's my air over there. And it's a uniform body, so I know it's only the face area times the depth. And I calculate it to be almost 2 liters of air that's trapped inside of that tank. Second question I'm going to look at is the case of the 3 cylinders that is stacked tightly against each other. There is a crevice between it. You will see it's almost, it's got a triangular, almost a curvy triangular shape, and it goes all the way down. So if I had to fill that with resin, because that's what they say you do, they're going to fill that gap with resin. And if you had to remove the 3 cylinders, you will find that the resin volume will look like that. Once again, it is a uniform body. You will see it retains its shape all the way down. So I only require the facial area, the area of that turquoise, and then I require the depth, which they told me is 30 centimeters, and I will have the volume. So how do I calculate that facial area, that turquoise area? I'm going to just look at this object from above. There it is. Here's my diagram over here. And I am going to connect the 3 circle centers, thereby creating a triangle. They give us the radiuses of the circles. The small one's radius is 2, the big one's radius 3. And when I extract the triangle, it looks like that, right? So I have a triangle. I know that the 2 angles alphas will be the same, beta above. Everything is pretty clear here. What am I after here? Well, if I look at the situation, you will see that the area we're after, that turquoise area, is the triangle minus 3 sectors. Sector 1, this is also sector 1, it's 2 of them because they'll be the same, and let's call that sector 2 over there, right? So if I have to subtract those 3 sectors from the triangle, I will be left with the turquoise area. So I'm after sector calculations. Now, if I want to do that, the area of a sector is a half r squared theta, where theta is a radian measure. So I need to know what the alphas are, and I'll need to know what beta is. And the only way I'm going to do that is by dropping a perpendicular, as I show here in the diagram on this left-hand side. Now I can use Pythagoras, because I know that if I drop the perpendicular, there you go, 90 degrees, I'm going to bisect the bottom line, which is 3 and 3 each. And if I use Pythagoras, I calculate that h is 4 centimeters. I now have a perfect way to calculate the area of the triangle, which I do as a half base times perpendicular height. So I now know what the area of the triangle is. But more than that, because I now know what h is, I can go and calculate alpha. Right, I'm going to use that triangle over there. So what is sine of alpha? Well, it is my h over 5, 4 over 5, 0.93. There you go. So now I know what alpha is. Of course, that it goes for the other triangle as well. This will also have alpha, so those two will be the same. And if I calculate the purple area of that one sector there, the purple's area, it is half r squared theta. I calculate that area to be 4.19. Of course, the yellow area will also be 4.19. All that remains now is the sector of the smaller circle. So I need to know what beta is. So what's beta? Well, we know that the angles of a triangle add up to 180, but in this case, since we're working with radians, 180's radian equivalent is pi. So it's pi minus 12, 2 times the alphas, which leaves us with 1.29. So the blue area, half r squared theta, lands us at 2.58. I'm now ready to calculate my turquoise area. It's the area of the triangle minus 2 of the sectors of the bigger circle minus the sector of the smaller circle, leaving us with that turquoise area of being 1.04 square centimeters. Now we're going to go over to the volume calculation. Because this is a uniform body, all I need is the depth, which is 30. And you are done.